Yes, when you try to divide by zero in mathematics, you get infinity, or they call it also a singularity. So at time equals zero, in the beginning of the universe, we also say that's a singularity. So bringing in the religious aspect again, and science is no position to argue anything different. You could say perhaps instead of all heaven breaking loose, it may be, all hell breaking loose, maybe heaven breaks loose. And maybe there is something with an infinite mind to create the finite. So this is where you might say that religion complements, or complements science. Now, I didn't mention in the first part, in the introduction as well, why, if there's an indication that there are two different domains, the spiritual and the physical. Persinger did an experiment in Laurentian University in Sudbury, Ontario, where he took students, and unbeknownst to the students what the experiment was going to be about, he put helmets on their heads with magnets to measure their brain waves. Then he put them in an isolation booth devoid of any ambient electromagnetic radiation, and of course without the sense of touch or sight or sound. And he observed what happened to their brain waves. And he noticed that the left brain was shut down and the right brain became more active. Then he asked the students to come out, and when they came out, 4 out of 5 said that they had out-of-body experiences where they felt they left their own body and saw tunnels of white light. Some said they felt someone was beside them or behind them. Some said they saw demonic creatures. Some even said they saw God. And as a result, it's been nicknamed the God helmet. So this is another reason why you can say maybe science cannot answer everything. There are two different dimensions, the physical and the non-physical. Now going back to the beginning of the universe then, where science cannot say how the universe started. I mean, there may be some speculation that they have of how the universe came into being, but they have not had any empirical evidence or observation. And you should take your ideas back into the lab and test them out. And to my knowledge, no one has taken them back to the lab and created a new universe. And if they have, they haven't come back to talk about it. So here's where religion really is complementary and has the answer to how the universe came about. Now they also said that you need a force, all the forces, everything then is in the size of say, a molecule or an atom. And it would be all the forces, a super force. Well, again, with a religious connotation, we say that God is omnipotent, all-knowing, and all-powerful. So in science, it's say all the forces were one, called a super force. And at the first Planck time, the force of gravity separated from the super force. And at 10 to the minus 35 seconds, the strong force separates from the super force. And at that time, the universe goes through quite a expansion. expands faster than the speed of light. And how can anything go faster than the speed of light? The speed of light is constant, 10 to the 10th centimeters per second. You know that's the case because if you look at a planet coming towards you, measure the light, and measure the light again after the planet goes by you, going away from you, it's the same. But at that time, it's not something going through space. It's space itself that is expanding. So that doesn't violate any physical or scientific fact. Then at 10 to the minus 12 seconds, the electromagnetic force separates. Also another force called the weak force separates out. Now, if you're in that room and no one seems to notice you, well, you do have radiance. So you're a radiant person. So maybe they should. But you're not all that radiant. It would take millions of years times the age of the universe for you to radiate away, for your atoms through radioactive decay to radiate away. It's nevertheless important. Without it, you'd probably die. Because it keeps the center of the earth molten, and the center of the earth is iron. And when the earth rotates, it sets up an electromagnetic field or shield. That's why you get your north magnetic pole and your south magnetic pole. And that shield protects you from harmful solar radiation and harmful cosmic radiation. It also protects the atmosphere from being blown away by this solar radiation. And the atmosphere is important because, of course, you need it to breathe, so the oxygen. And also, it mitigates all the harmful material from space falling through the earth and killing you. The meteorites, asteroids, comets. Now, most of them are burned up in the atmosphere. Some get through, and there's cases where some big ones even get through, and we'll talk about that later. Now at that time as well, I say 10 to the minus 12 seconds, you get your electromagnetic force. That separates out. At that time also you get all your particles, and you get antiparticles as well. For every particle there's an equal and opposite antiparticle. For an electron there's a proton. For an up quark there's an anti-up quark. And when particles and antiparticles come together and collide, they annihilate each other. So in that first second you've had energy and matter being exchanged time and time again. At 10 to the minus 1 second, or 1/10 of a second, your protons are created. But then at 1 second, something really important happens. For every billion antiparticles, you get 1,000,000,001 particle. So you have 1,000,000,001 chance of getting through that. Because if you had any antiparticles, you wouldn't exist. Antiparticles and particles turn into energy. And science doesn't know why that is the case. They try experiments where they They change energy into mass, or mass into energy. And this always comes out to be exactly the same. There's no one particle left over. And that is, if that weren't the case, then you wouldn't exist, nor anything in the universe. It'd be all energy. Now, here's another example where science, you think science is always true. If it's a scientific fact, then how could it change? Well, before 1905, all the scientists thought that matter and energy were the same, were different, sorry. But then Einstein came along in 1905 and said, no. Energy and matter are the same. E equal mc squared. Your energy is equal to your mass, or amount of material you have, times the speed of light times the speed of light. So even the consensus of all the scientists can be wrong. Now we do have some evidence. We don't have any evidence about time because but we do have some evidence of how particles are created. And normally we have to take it back, as I say, into the lab and test your ideas or your hypothesis. So the lab in this case is the Large Hadron Collider in CERN, and that is in Switzerland. It's one of the most marvelous pieces of equipment that exists. It consists of 27 kilometers or so, a loop underground in CERN in Switzerland, where they have large electromagnets, and they accelerate particles in one direction at near the speed of light, and then another group of particles, maybe protons, at the speed of light going the opposite direction, and collide them together. And when they smash up, then the parts fly off, just like in a car roller derby. When you hit the cars, the parts fly off. At first, there was such a zoo, so many particles, they call it zoo, particle zoos. But then they narrowed it down to the particle theory, which explains all of the different forces and all the different particles that you ever want to know or ever want to know in the world. As I say, there's 3 levels of quarks: the up and down, and the charm and the strange, and the top and bottom. And for each one of those pairs of quarks, there's a lepton. For the up and down, it's the electron, and for the other two, it's the mu or muon and the tau. And then there are the 4 forces: the force of gravity, force of strong force, the weak force, and the electromagnetic force. And for each of those forces, there's a boson. And the boson is the particle that is exchanged and gives the force their force. For instance, in the electromagnetic force, the boson is the light, or the particle, light, the photon. So when you take a magnet, the north end of a magnet, and try to push it towards the north end of another magnet, there's a resistance. Why? Photons of light are being exchanged between the 2 magnets. That's the boson, responsible for the force of gravity. The boson for the strong force is the gluon, and the bosons for the weak force is the Z and W bosons. The one for the gravity is a graviton. Now they could use the Large Hadron Collider to get, for instance, the quarks at going back to 10 to the minus 12 seconds. But to try to get the graviton, you'd have to have a collider the size of the solar system to get enough power to find that. But they had another piece of equipment which they've just developed called the LIGO, LIGO, uses interference waves of light, of waves of radiation to find the graviton. And they discovered, not too long ago, gravitational waves, which means there must be the graviton as well. Now they figured there should be an extra boson required to give mass to the other particles. A guy called Higgs proposed this back in the mid-20th century, and in 2012 they found the boson, which they now call the Higgs boson. It took that long because one of the reasons would be that they had to increase the power and in order to get enough power to find the Higgs particle. And whenever you have a theory or postulate or hypothesis, and you have that predicts something, and then it comes true, that gives the theory more credence, or something closer to the truth. And the same with finding the graviton. So you have then all these particles, and you have the extra particle left over after 1 second, which went on to create all the universe, and you have a billion to 1 chance. But what's it's so hot and dense that all the particles, for instance, protons, the photons, electrons, can't combine. It's like a plasma. It takes 380,000 years after that for things to cool down enough for that to happen. And then you get an electron being captured by a proton. So what do you have? That's where you get all your hydrogen from. So your hydrogen that you have, which is over 50% of you, your atoms, is 13.8 minus 380,000 years old. So you, physically at least, are that old. That's where you got most of your atoms from. And you thought you probably were under 100 years old. Well, most of you is 13.8 minus 380,000 years old. Now, where do you get all then your other atoms from? Well, maybe you can thank your lucky stars where you got your hydrogen from, but not really. Hoyle was one of the scientists that figured out where you got all the other material from. But Hoyle, the theory that we've been talking about is the Big Bang theory. Hoyle, who was a leading scientist, didn't like that theory. He had what is called a steady state theory, where the universe is steady as she goes. Same number of stars being created as disappearing. He didn't like the other theory, and he called it a Big Bang theory derisively, but the name stuck. So the Big Bang theory was named after someone that didn't believe in the Big Bang theory. So you have all this hydrogen being created then at 380,000 years after the Big Bang. What happens to that? Well, over the next half billion to billion years, you get more and more hydrogen, and it gets denser and denser. And at the center, the force of gravity becomes greater. So great that it overcomes the electromagnetic force that keeps your from your atoms apart and you from falling through the earth. So they takes out the space in between the nucleus and the circumference of the atom. They touch. The two protons touch, and that's fusion. It creates the next element in the periodic table, hydrogen. It has 2 neutrons and 2 protons and 2 electrons. But it also gives off a lot of energy. There's extra mass or energy left over. Like you get in a hydrogen bomb, it's a fusion bomb. So you have all this energy, and it's opposing then the force of gravity. So there's a tug of war between the two. And also you have all this energy being given off. So what have you got? I could say Judy Garland, but I will say A Star is Born. What's the nearest star that you have towards the Earth, towards you? Do you know its name? You should know its name. It's called the Sun. So the Sun is a star up there converting hydrogen into helium and giving off lots of energy in the form of heat and light. Now a star then that is 8 times or so more massive than our Sun, when it uses up all the hydrogen and converts it into helium, then it starts to fuse the helium atoms together. And so on. It keeps on. Then when it uses that up, it uses the next element in the periodic table, and so on until you get up to iron. Now you probably got all your oxygen and your phosphorus and your carbon before that. But when it tries to fuse together 2 iron atoms, it doesn't give off energy, it requires extra energy. So there's no force keeping the force of gravity at bay, and the star collapses almost instantaneously with such force it blows itself up into what is called a supernova. And that produces more energy or light than all the other stars in the galaxy combined. Some 100 billion to 200 stars. And with all that energy then, it's able to fuse together hydrogen, the iron atoms, and most of the other heavier elements in the periodic table. Now a star, which is 100 times more massive than our Sun, when it goes into a supernova, I should say first, that when the supernova occurs, it leaves behind a core. And the core is it's very dense. It has atoms with all the space taken up. It's called a neutron star. And 1 teaspoon of that would weigh more than all the cars in North America. Now, I didn't try that experiment because when you put the spoonful of the neutron star in your hand, force of gravity is so great because the mass is so much. As I say, I tried to test that out, but I found that if you took 1 teaspoon of the neutron star, it fell right through my hand because if you recall, the electromagnetic force stops anything from going through your hand. But in this case, the force of gravity was so much greater than the electromagnetic force that went right through. And I gave up counting the number of cars in North America as well. Now, a star which is over, as I say, 100 times more massive than the Earth, when it explodes, it leaves behind a black hole. And a black hole is so massive that even photons of light cannot escape. That's why it's black. So the escape velocity from a black hole is more than the speed of light. Now they figure recently that to get the most heaviest of the elements, that happens when either 2 neutron stars or 2 black holes collide. So all this material is being created even within the stars and with the supernovas, spewed into space. What happens to that? Well, the force of gravity takes over again, and the second generation stars are being created. Our star, which was created some 4.6 billion years ago, could be a 3rd or 4th generation star. Now, 10 years ago, they said it was 4.5 billion years ago. So again, they had to modify with a new piece of evidence, perhaps, to change that scientific fact to some other scientific fact. Now, first, the lighter elements would have formed the sun, and the other elements and material would have surrounded the sun going around. Now, something the size of dust, it would use the electrostatic force to bring those together. And then gravity would take over. At that time it would be very chaotic. There would be a lot of different materials smashing into each other, breaking itself up, and gravity pulling it together again, forming bigger and bigger entities, until you get up to, say, planets. And even planets were bashing into each other, demolishing each other. There'd probably be 100 planets. And of course there are a lot of dwarf planets too that we're discovering. Probably more dwarf planets than there are planets. But even some of the planets, when they're hitting each other, would demolish each other. There was one the size of, say, Mars that hit, they call it Theta, that hit the Earth. It hit at the right angle, 45 degrees, and so it didn't demolish it, or it didn't just bounce off, but it put out a whole chunk of the Earth's crust into the space, which went around the Earth, and gravity brought that together to form our moon. So our moon is part of the Earth. And at that time, the Earth would have been almost molten because of all the bombardment, and the moon would have been very close to the Earth. And a lot of material going around the moon as well, because it was cooler on the other side. More material would have settled on the other side of the moon, which is why the crust on the other side of the moon is some 25 or so kilometers thicker than the crust on this side. When you go around the moon, if you have a chance to go around, check it out. There's one fairly big black spot, a lava lake. Whereas on this side, there's several. Because this side, the crust can crack and the lava can come up through it, whereas the other side is, except that one occasion, very difficult. That's why you see the man on the moon. Or you can look from top to bottom and you see a female and a male kissing each other. So that is maybe why we think of the moon as being romantic. And the moon is important for you and most complex life, because you figure that stabilizes the earth, and without that it would be difficult. So you got down to the moon. That's how you got to the moon. But there still doesn't explain how you came alive. Because the moon and the earth would be so hot and even molten that for the next 500 million to 1 billion years, more like, life could not form. But then when life did form, and science does not know definitively how that happened, they have some speculation or some hypothesis. And they try to produce life in the lab. But full-grown life, no. And they can produce maybe some amino acids, which are some of the components of life. But to actually produce life, or to see life actually being created, no. It does not have a definitive answer how that happens. As I say, they could have a hypothesis, but in order to become a true theory or a scientific fact, you need to have empirical evidence or observation and prove it in a lab. But life then was pretty boring anyhow. It would be only one-celled animals or plants. And then they gradually come more and more together to form multi-celled organisms. Just by cloning each other. But it wasn't. When did you first have sex, by the way? I'm sorry to ask such a personal question, but it's the kind of sex that we think of really 500 million years ago. And then life did proliferate, all different kinds of life. And there were plants and animals. And there's somewhat of a symbiotic relationship between the two. Figure that the life started even on Earth, and also now see that life could have started deep in the oceans from chemical reactions given by volcanoes giving off these chemicals deep down in the ocean, where there is no sunlight. There could be no photosynthesis. But life came from the ocean onto the land and planets. These are a process called photosynthesis, which takes energy from the sun and oxygen and carbon dioxide from the atmosphere and produces oxygen. Animals, on the other hand, take oxygen from the air, and through a process that we'll discuss briefly, very shortly, gives off carbon dioxide. And also, when plants die and rot, normally, they give back some of the carbon dioxide that they used to grow previously. Now, when animals grow, well, you get cells. You get genes. You have your genes, for instance, from your mother and biological mother, half from your biological father. And genes consist of cells, and there is a core in the middle of the cell, deoxyribonucleic acid, DNA. And that's what gives you all your physical characteristics. most of your physical characteristics. Your color of your eyes, the color of your hair, size of your nose, how big you can get, etc. And what happens there is your DNA looks like a ladder with rungs in between it. It consists of actually 4 different chemicals. And when you grow, it's twisted, so it's called a double helix. When you go, there's a split down the center of the ladder, and then the new left or new right comes together with it to form another cell. And that happens billions and billions of times, except perfectly, the left side matching the right, except when it doesn't. Perhaps there's some radiation, the cosmic radiation gets through, bashes out a piece of your DNA on one side, and that then forms a new piece of DNA. And your DNA, as I say, gives you all your characteristics. So that, with your new DNA, could mean that your physical characteristics changed too. And that process we call mutation. And then when you pass on your genes, which has your DNA, to your offspring, then they may have different characteristics. So, after a half billion years ago, I think you had all these plants, and one smart-ass plant, he thought he could be bigger and better than the rest of the plants that stayed underground. So he grew higher to capture more of that beautiful sunlight, right, and energy. But when he died, he didn't rot. He just fell down and was compressed and compressed over millions of years into coal. So that's where you get all your coal from. Now during that time then, since the trees didn't give back carbon dioxide into the atmosphere, it would have been much more rich in oxygen than it is now. So your insects, which lived at that time, could have grown much bigger, because they breathe through tubes. And when they breathe through the tubes, some of the oxygen is absorbed in the tubes. But if there's more oxygen, the tubes can be larger, therefore the insects can be larger. And for instance, a centipede could be the size of a crocodile. And we've had a lot of close calls where life itself could have been knocked out or become extinct. 5 major ones, and you see the difference in the ages of the Earth, Triassic, Jurassic, Cambrian, so on. Often they're associated with close calls, where much of the life has been exterminated. 225 million years ago, happened in Siberia, not Siberia, Siberia, where it became so, probably through volcanic activity, heated up so much that the coal started to burn up. At least this is what some scientists think. And that caused such a lot of commotion that 70% of all living things became extinct. 90% in the ocean and the rest on Earth. So luckily you got through that. That was pretty close call for you. And then they had the age of the dinosaurs. Oh, and they lasted around, ruled Earth for 160 million years. You were around too, like a mammal, and you had to stay underground in the daytime, because if you came out at night, or in the daytime, sorry, you'd be eaten by the dinosaurs. But you could stay underground at night because you're warm-blooded. Whereas dinosaurs are cold-blooded and they need heat or light in order to move around. So you would have had to stay underground in the daylight and come out at night to eat. Otherwise, you would have been eaten by dinosaurs in the daytime. Now, during that time, there was one continent called Pangaea. The age of the dinosaurs, I should say, lasted to 65 million years ago. And during that time, there was one large continent called Pangaea broke up into the more or less the planets you see now. Now you can sort of speculate and look and see that, say, South America fits into Africa. But before mid-20th century, no one really thought about that, or said, oh, they might have said, oh, that looks kind of strange, or whatever. But they didn't know. A guy called Wagner, he looked at it and he said, yes, it looks like the continents fit together like pieces in a jigsaw puzzle. But he went further. He got empirical evidence. He saw that the fossils of animals and plants on this side of the Atlantic were identical to the fossils of the plants and animals on the other side of the Atlantic, and existed nowhere else in any place on the other parts of the other continents. He looked at the land formations and found that they started on one side of the Atlantic and continued on the other. And even sedimentary rock, which has different layers of different kinds of, well, with different thicknesses of each layer, matched up perfectly with some sedimentary rocks on the other side of the Atlantic, indicating it must have been a split right there. And fourthly then, he looked at the fossils in the north and found that they had to have lived in the south. So the land itself must have moved from the south to the north. So for all these reasons, he said, his theory was that the Earth split up into the continents from one large continent. Was he heralded as the greatest geologist or greatest scientist of his time? No. The exact opposite. Far from it. He was vilified. He was made the laughing stock of the geological and scientific community. They said, this is ridiculous. They, in their opinion, and the consensus of all the opinion, said this is nonsense. And science should follow the evidence, no matter where it leads. They ignored the evidence. They just brushed it off. Franklin died not knowing that his theory would ever be, he'd be vindicated. He was going off searching for more evidence in Greenland, and he saw some people rescued, or helped some people in the snow in Greenland, walked off to never to be seen again, not knowing that his theory would be accepted. It remained for another couple decades to another scientist said to explain how that would happen, that the continents are on plates which move around and on top of the magma. This is why you get all the volcanic activity and earthquakes where the plates meet, or why you see the Himalayan mountains formed when India came from Africa and smashed into Eurasia and formed the Himalayan mountains. That's called the continental drift theory, which everyone believes in now. So again, even scientists and the consensus of opinion from scientists can be wrong if they don't look at the evidence. You need the evidence to support their consensus or their theories or their speculations. In this case, it wasn't a true theory. So, what happened 65 million years ago? Another event. Not so good for the dinosaurs, but good for you. Because Jupiter, the largest planet in the solar system, more massive than all the other planets combined, let down its guard. Normally, through the force of its gravity, because of its force, because of its mass, rather, it would attract a lot of the meteorites, meteors, comets, and asteroids before they hit the Earth. 65 million years ago, it let through a big whopper, so big it got even through the Earth's atmosphere, and it landed at the Yucatan Peninsula in Mexico. Caused quite a stir. All the force caused a lot of heat, which burnt off a lot of vegetation, and all that material was. Yes, it took many steps for you to get here, and many of which the science cannot answer. For instance, your parents had to meet and produce you. You get half of your genes from your biological mother, half from your biological father. And then their parents or your grandparents had to meet and pass on their DNA to your father and mother. So you are 1/4 of your grandparents in terms of your physical characteristics. When someone says you look just like you're just like your dad or just like your mother, well, literally you're 1/2 physically, and 1/4 your grandparents. And over 100 years, that would be 4 generations. So you'd be part of 16 different people. And over 1,000,000 years, would that be 1,600? You can work it out. And over 1,000,000 years, 16,000 different people that you were part of. And then you're on a planet, one of, is it 7 now? Where, as far as we know, only complex life like you exists. Now, they've been trying to search for other intelligent life. Carl Sagan, for instance, a scientist responsible for SETI, search for extraterrestrial intelligence. They sent up 2 gold plates on the Voyager, 2 Voyagers, with the location of the Earth. They use quasars, which are neutron stars that flash, to pinpoint where the Earth is. And several languages, as many as they could put on, of different people from the Earth, in case an advanced civilization would intercept the satellites, and at least they would know that we existed. Now, recently, they've looked at other stars, and they found that most of the stars that they look at have other planets. So they're looking for stars which have planets located in their Goldilocks position, like Earth, not too far from the sun, their sun or their star, so they wouldn't, the water wouldn't freeze, which we figure life needs water, or not too close so the water would evaporate. And they found a few candidates. But even looking at the solar system, they now see that some of the dwarf planets, and there are probably more dwarf planets than there are planets, they have ice, frozen water. And underneath that, they may have water, which has at least microbes. So there's a possibility they could even find life on the in the solar system. But so far, no life has been found, and science does not even have a definitive answer how life really started. As I say, they have some hypotheses, but in order to have a true scientific fact, you have to observe it or be able to create it in the lab. And the solar system is one of at least 100 to 200 billion stars in the solar system. And the galaxy, in the galaxy, and there's at least 100 to 200 billion galaxies. So there's been a lot of different events over a different time. For instance, you got all your atoms, other than hydrogen, between 13.8 billion years and 4.6 billion years. So you could have one carbon in your finger that is 12 billion years old, and another carbon in your other finger that's 6 billion years old. And it could have come from different stars and solar systems and different galaxies. So a whole lot of different events over a whole lot of different time is possible for you to be here. And then for your hydrogen to be here, the part of the other parts of you, you had to survive the first second, where you had a 1 billion to 1 chance of getting through that to produce your particles. Because if you had any antiparticles, you would not exist, nor the universe. And here science does not know why that happened. It can't reproduce that in the lab either. And then, in the first second, you got your force of gravity, which keeps you grounded, and your electromagnetic charge, which keeps you from falling through the earth, and your strong force, which keeps you from falling apart, and your weak force, which protects you from the solar and cosmic radiation, harmful, and gives you the atmosphere, at least protects the atmosphere from solar radiation, and that protects you from comets, asteroids, meteors, from coming down and killing you. That could, although it doesn't protect all of them, we'll see that later. Well, we saw that already, didn't we? And then at time equals 0, which science does not know how that happened. Because according to the scientific theory, the smallest unit of time is 10 to the minus 43, 1 Planck time. So how can you get down to time equals 0 if time can't be lower than 1 Planck time? And again, science does not have the answer for that. But you could say that you need religion to complement science. Because you could say that it needs to be something infinite, an infinite mind, which we call God, and something omnipotent to create all the forces, super force, and so on. The other thing that science cannot understand is why all the forces and all the constants are exactly as they are, as though they were designed to be that way. Because if they weren't any different, some of them, you would not exist. One example would be the force of gravity. If it were any lighter, or less, then it couldn't have brought together all the hydrogen after the first second, or after 380,000 years after the Big Bang. and the universe would be simply hydrogen. Or if it was any stronger, once it produced the hydrogen, it would be so strong it would bring it back together again through the force of attraction into a big crunch. So if that were any different by a small amount, you would be here. And when they look at the universe, they see that it's expanding. Why is that expanding? Well, Einstein put in lambda in his general theory of relativity that would allow the universe to expand or contract. And he took it out because he, like everyone else, said, well, doesn't make sense. So, the universe is just there. It's always been there, always will be. And he said it was the biggest mistake in his life by taking it out. And the biggest mistake, of course, was thinking it was a mistake. And now they put it in. And they look at how the universe is expanding, and they found that it's not contracting like they would think. The force of gravity would eventually take over and bring everything back together into perhaps a big crunch. But no, it wasn't slowing down, it was accelerating. And that really surprised them. Why is it accelerating? Then there must be something counteracting gravity which would pull it back together again. They don't know what it is, so they call it dark energy. So that's what's overcoming the gravity, starting at least some 9 billion years ago. Now they can speculate or hypothesize that space is not empty. It's full of virtual particles and antiparticles. And when these particles come together, they form energy. They annihilate and form energy. And in order to make sense of how fast it's accelerating, they need to have this dark energy to be 70% of the universe. And even then, when they calculate using all the science theories that they have, and compare that calculation to what is actually happening, they were out by 10 to the 120. That's a colossal mistake. So that points to maybe that the science doesn't really know all about the fundamental questions about how we got here and exactly what's happening. They also discovered that they don't have enough gravity either. So you need more mass. How did they come up with that? Well, when a skater spins, when they put their arms out, they go slower. When they bring their arms in, they go faster. Then that's same with like the solar system. Pluto goes around the sun much slower than Mercury. But when they looked at how the stars go around the center of the galaxy, then they found that no, this doesn't apply. They needed more mass or more gravity, 4 times as much, and they don't know what it is. So they call it dark matter. It does not consist of molecules, atoms, quarks, etc. So they're in the dark about that. And then also needed to explain how gravity brought all of the hydrogen together to form the stars. So basically science is in the dark about 95% of what's going on. And so maybe there does need to be another theory to explain the current situation. Now, if we look at some of your other physical characteristics, what would you say would be your weight? Now before before the 1600s, really people didn't understand what the weight is. But Newton, back in the 1600s, he saw an apple fall to the ground outside in the orchard outside of his house. And he said, it didn't fall on his head, by the way. He said, well, that's an attraction between the apple and the earth. And he came up with a formula. He said it's proportional. Any two objects, whether it be the apple, earth, or any two objects at all, it's proportional, if you like, equal to the mass of, or the amount of material in the one object times the mass of the other object divided by the square of the distance between the two objects. So the force of attraction between the apple and the earth is equal to the mass of the apple times the mass of the earth divided by the difference, divided by the length between the center of gravity of the apple and the center of gravity of the earth squared. And what is that force? Well, that then is gravity. So what is gravity is? So if you're in that room and you're really not much at all, I mean you're mostly space, and you're really not all that you're not really all that radiant, you are somewhat attracted. People are attracted to you, and you are attracted to them. Now you might say, okay, I could be attractive, but if you look at a distance, you can't see any flaws. But if I come closer, you'd see, well, probably overweight, and I wouldn't be that attractive. Not really, no. The closer you are, and the more bigger you are, or the fatter you are, or the more you weigh, the more attractive you are. And that attractiveness is equal to your mass times their mass divided by the distance between you squared. Now you can't really notice that because your mass and their mass aren't that great. But if you go outside, a mountain would be more attracted to you, or the earth itself would be more attractive. And to check that out, just slide something between you and the earth. Let's call it a scale, and you'll see how attractive you are. And what do we call that? Well, that's your weight. So your weight is equal to your mass times the mass of the earth divided by the distance between you and the center of the earth squared. So supposing you wanted to lose weight then, well, why can't you just climb a mountain? Because the distance there would be larger, and then you're dividing by the distance, and so you'd lose weight. Oh, you want to gain weight, go down into a mine, and the distance there would be less. So therefore you would weigh more. But if you look at the earth and compare it to, say, a billiard ball, and the surface of the billiard ball you see the surface of the billiard ball to the surface of the earth, you can see that the differences that we're talking about there between the top of the mountain and the bottom of a mine are so small you wouldn't notice it. Probably the same if you go to the equator, because the earth is not perfectly spherical. It bulges a bit at the equator. Therefore you should weigh a little less at the equator than you do at the North Poles. But again, probably not enough to notice or measure. If you really want to lose weight, go to the moon, because the mass is only 1.2% of the earth. So you would only weigh 1/6 as much as you do on the earth. When you saw Armstrong on the moon, when he was walking, he was almost hopping, even though he had some heavy equipment on his back. So even though the distance between the center of the moon, and you would be less. Since the mass is so much smaller, you would only weigh 1/6 as much. So if you want to break some Olympic records, like a high jump, go to the moon and try it out there. You could really smash the records. But wait, did I say you're attractive? Well, no, you fall for that person. And here's where I might be accused of being somewhat sexist, because women have fallen for every man that they ever met, and will fall for every man that they will meet in the future. And do we call them fallen women? But men will fall for every female that they have met, and every single female that they're going to meet. We don't call them fallen men, do we? So, but to be fair, men would fall for other men as well, and women will fall for other women. Why is that? Because they change the space around them, and you fall into the space that they've created. Like if you stand on a trampoline, and you put a basketball on the side of the trampoline, the basketball will fall for you. It falls into the indentation that you've made in the trampoline. So in 1950, this is what Einstein said. Gravity is not the force of attraction between you and the Earth. Nor is your weight. It's a warp in space-time. And he came up with that with a thought experiment. Here's another thought experiment which maybe will give you an idea of what he's talking about here. Take a rubber sheet, stretch it out, and representing space-time. Space and time are so interrelated that we can put them together. But think of it first as just space. Then take two ball bearings, one large one and one small one. The large one representing the Earth, and the smaller one representing the Moon. Put the large ball bearing on the rubber sheet, and it forms an indentation in the rubber sheet. Or the Earth forms a warp in space-time. Roll the smaller ball bearing towards the larger ball bearing, or the Moon towards the Earth, and it'll, depending on the mass of the Earth and the mass of the Moon and or the ball bearings, they will either go right by, and how fast you roll it, and how close it comes to the other ball bearing, it'll go either go right by, or it'll hit the indentation and be deflected and keep going. Or it'll hit the indentation, or in the case of the Moon, it'll hit the warp and go right around the other ball bearing, or the Sun or the Moon will go around the Earth. So it's not because the Moon is attracted to the Earth, or the small ball bearing is attracted to the larger ball bearing. It's because of warp in space-time. So that refutes then that refutes Newton's law of gravity. He said no, it's gravity, and also his other law, the law of momentum. He said that if something goes, or if something is moving, then there must be something to stop it. There's another force. Otherwise, it would keep moving. Law of momentum. Aristotle 2,000 years ago said, no, everything will stop. It's a natural thing for something to stop, and you need God to get it moving and the hand of God to keep it moving. So with Newton, he would say, well, take a cannonball and a cannon up on a mountain and drop the cannonball by the cannon. It drops just like the apple and drops to the ground below. But if you shoot the cannonball out of the cannon, it would go a kilometer, mile, before it falls down. Shoot it harder and go halfway around the world. Harder again and go all the way around the earth before it falls. Harder again, it'll keep on going and right around the earth. If there's nothing to stop it, and there's hardly any friction, so it would keep on going around. So that's why the moon goes around the earth, and the earth goes around the sun. Einstein says, no, it's just the warp in space-time. So is Newton wrong? Yes and no. Because we use Newton's laws of momentum and law of gravity to put men on the moon and to shoot satellites farther than they would go under their own steam by using the force of gravity of the other planets. So it's, for everyday use, it's still used quite commonly. So here's an example then where even if a new theory replaces an old, we can use the old as long as we restrict it to areas where it works. And it doesn't work, for instance, to explain how Mercury goes around the sun. Mercury, being closer to the sun, is more influenced by the warp caused by the mass of the sun. And you need Einstein's equations to more definitively explain the motion of Mercury around the sun. Now, we've been talking about space, but Einstein said it's space-time. So time it also changes when you approach a large mass. Not just space. Time slows down. What? That doesn't make sense. How can time slow down? We don't notice it because we're at pretty well in the same position within the warp caused by the Earth. But if we go farther away from the Earth, we'll find that time does change. For instance, going to satellite. Satellites farther away in the warp, and therefore it runs faster than time on Earth. You'd have to have an atomic clock to measure it, but yes, it does. And is that important? Well, if you want to go someplace and use your GPS, yes, it is. Because without incorporating the difference of time between the satellite and the Earth, and your GPS uses satellites to locate you, you would be out. Your GPS would be out in 2 hours, and you'd get lost. So, although we don't think of it and use Newton's laws for everyday use, most of everyday use at least, it is nevertheless more accurate or closer to the truth than Newton's. And that really, even though it's weird, we have time and space can change. It's really how we define how the world works. So it's the Einsteinian view of how the world works. And quite important, along with this other law, E equal mc squared. But did he get a Nobel Prize for that? No. No, he didn't. Even though he's the most famous scientist. But he did get a Nobel Prize but for his contribution to another world theory, or how the world works, at the quantum level, at the smallest possible level. He discovered the photoelectric effect. When light hits an atom, it gives off electrons. And that's when you try to walk through an elevator door and it starts to close, it'll open again. Or the garage, when it starts to close on top of a car, it'll open again. And so you can thank Einstein for that. And he didn't like the other world vision, because quantum mechanics uses probabilities. It's not deterministic like his laws. One of the founders, of course, was Planck. He said, time and space, or time and length, cannot be cannot be divided down continuously. It's discontinuous. Whereas Einstein's laws, no, there's nothing to stop it from dividing things down forever. And one of the other founders would be Heisenberg, principle of uncertainty. You can't be certain of any two things that are related. If you're certain about one, you'll be less certain about the other. For instance, if you want to know the speed of a particle and the location of a particle, the more you try to find out where it is, the location, the less you'll be able to determine how fast it's going. And vice versa. Not because you have problems measuring it, but that's reality at the quantum level. Just to show the weirdness of the quantum level. You thought Einstein's theories are weird. Well, just wait to hear this. And it's the classic one, you may have heard of the double slit experiment, where they pass light through two slits and see what happens on the other side, on the wall, say, on the other side. Well, you think you just get to two lines of light. No, you get several lines of light. Because light can either be a particle or a wave. And as I mentioned before, look through your two fingers with one eye, and you'll see faint lines in between them if they're close enough. And that's because it's a wave. The waves are interfering, the light waves are interfering with each other, like two rocks when you throw them into a pool. So those lines that you see on the other side are interference lines. Okay, well, maybe you can understand that. But if you look at the light before, or measure it before it goes through the slits, then you don't get several lines, you just get two. What's that mean? Well, somehow the wave is changed back into a particle, and so it goes straight through and makes those two lines. So is there someone out there watching everything? Otherwise we'd all be waves. Another area where maybe one needs religion to understand what's going on. And so we say in religion, if God can see a sparrow, we know someone is watching you. So somebody's out there watching to make sure that you change into particles. What's even weirder yet, though? If you send one photon at a time through and towards the double slit, then it should either go through the left or the right, so it can't interfere with it. And what do you get on the other side? You should only get one over time, one or two lines, whether it goes through the left or the right. No. You get several lines. What's happened? Well, has one photon interfered with itself? Is time different so that this can happen? Again, science cannot know why, they just know how. And they use quantum mechanics as one of the most reliable and powerful tools that they have at their disposal. And there's no contrary evidence to say that their theories of quantum mechanics are wrong. And they use the equations derived from quantum mechanics to get untold accuracy, 23 decimal places. And one of the persons that made that enable people to come up with those equations, make it so simple. Another founder, and the name escapes me right now. He said anyone that thinks they understand quantum mechanics doesn't understand quantum mechanics. And yet, as I say, it's a very powerful and accurate tool. But they don't even know why all these weird things happen. So does science then understand exactly what's going on? Well, not really. Einstein didn't like the quantum because he said God does not play dice, because everything's based on reality. And you don't really get what reality is, what we think reality is, until you combine all the probabilities in the macro level and what we think of more reality. It doesn't seem to apply at all in the quantum world. So here we have two different views, or two different world theories of how the universe works. And science, even though they are both can be called theories because they both have evidence to support them and no evidence to say they're wrong. And yet they're totally incompatible. Einstein's is deterministic. Quantum is probability. Einstein's is continuous. Quantum mechanics is discontinuous. You can sort of get away with it in quantum mechanics because the masses are so small and the force of gravity is so weak that you can sort of eliminate the force of gravity from quantum mechanics. Except when you can't. When the mass is small and strong, like in a black hole, which is small and massive, or at the beginning of the universe, which was small and massive. So they're looking for a theory of everything, quantum gravity, and as of yet they haven't found it, although they're trying to. They look at string theory to try to combine the two. But as I say, they need to have 10 dimensions instead of 3. And there's no way you can ever look at the strings because they're so small. You'll never find them. So, as Einstein would say, he didn't like the quantum because it dealt with probabilities. God does not play dice. He also said, until you can find a complete theory that combines the two, or something that replaces the two, then maybe you'll be closer to know the mind of God. So, science does not refute, really, religion. As a matter of fact, you think it's almost complementary to it in these cases. Now, the other attribute, is, of course, is your height. Now you might think, you might think maybe if you're a man, maybe if you're higher, women like the tall, dark, and handsome. So there may be an advantage to be higher. Or if you want to be a jockey or a gymnast, maybe it's an advantage to be shorter. A tennis player, two of the tallest tennis players were Eisner, almost. He's 6'10" or 11. And Ronick is only 6'5". They have the fastest, two of the fastest serves in tennis, because if they're higher, they have better leverage, and they can see over the net a little better, and hit the ball inside of the area where they have to. They also practice a bit as well. But several of the largest the players that hit the ball the fastest are quite high. So if you want to at least appear to be maybe taller, measure yourself in smaller units. So if you're only 1 meter high and you want to be closer to normal, measure yourself in centimeters. So you'd be 100 centimeters. And on the surface that seems bigger than 1 meter. It's 100 to 1. Or if you're 2 meters tall and you want to, that would be about the size of Eisner, I guess. You would measure yourself in larger units. So you're only 2/1000ths of a kilometer. I think that's right. So you seem to be shorter. Or if you want to be, you can measure yourself with the distance between the 4,000 miles between the center of the Earth and the circumference, and you'd be only 1/4000th of that distance if you're a meter. Or if you want to use units that are even larger, the distance between you and the moon, and that would be millions of miles. But there, because it's so, and you go beyond that, the sun and the stars, the distance is so big, you use a different kind of distance. You use light to measure your distance. For instance, when you're in a room, you think you want to, you ask the person, well, how are you? Well, you want to really know how they are at that time when you see them. No, you don't. You never can know how they are when you see them, because you see them several blank times ago. Billions and billions and trillions of blank times ago. The time the light left them to reach you. So you never see them as they are now. You want to see ghosts. Go outside and look up in the sky. You'll see several ghosts. Because several of the stars have already died, and yet you still see them. You see the light coming from them. Even though they're dead. So you're seeing their ghost. So when you look at the moon, you're seeing the moon as it was 1.2 seconds ago. So we call that distance 1.2 light seconds. When you're looking at the sun, you see that the sun as it was 8 or 9 minutes ago. So the sun is 8 or 9 light minutes ago away. You're looking at a star, and I can't remember exactly the distances. You would be thousands of light years ago, light years away. There's galaxy, some of the faraway galaxies, millions of light years away. The most distant star that they've seen through the Hubble telescope would be 13 billion light years ago. So your length then, or your height, is a small portion of the totality. It goes from 1.6 times 10 to the minus 35, the shortest distance, up to 13.8 billion light years. So you occupy a very minute part of that spectrum. The other thing that I didn't mention about time is that not only does time slow down when you approach a mass, and when you approach a black hole, it almost stops because the black hole is so massive. But also time varies on how fast you're going. Just think of this thought experiment. You have a friend and he's going on a trip, so he said he's going on a train. So you ask him, listen, I'd like to find out when the train goes 100 miles an hour, could you go up to the front of the train and throw a baseball 100 miles an hour? Well, if you ignore friction, then he should see that the ball goes 200 miles an hour. And then he said, wait till the train goes 3/4 the speed of light, and go up and throw it at 3/4 the speed of light. How fast does it go then? It can't go 1.5 times the speed of light because the speed of light is constant. It can't go more than it is, 10 to the 10th centimeters per second. Something's got to give. Velocity is equal to distance times time. It depends how far you go. Distance is equal to velocity times time. The distance you go depends on how fast you go and how long you go. But here, velocity, you can't go faster than the speed of light. So time has to change. D equals VT. So as your velocity speeds up, your time has to slow down. So we talked about before, you can see into the past. All you have to do is go out and look at the stars, and you're seeing what happened up to 13 billion years ago. But if you want to see into the future, all you have to do is get on a rocket ship and travel near the speed of light, or near the speed of light. And depending on how long you travel and how fast you go, when you come back, you'll see it into the future, because everything would have aged. Your friend would have been minutes, hours, years, 100 years, thousands of years, millions of years older. So you'll see how it will be in the future. So time travel in that sense is actually possible. Now, in summary then, I mentioned all the different steps you have to go through to get here, many of which science cannot understand. So it's miraculous that you got here at all the things that you had to go through, trillions and trillions of steps. So whether you think or not that would be miraculous, or you think it's just a random accidents, fortuitous as they may be, you're still a miracle that you made it through. The other thing science really doesn't understand is why can we get all these formulas? How can we derive all the different formulas from this reality or from space? First, is before 1905, there was the law of conservation of energy, law of conservation of matter, Newton's law of gravity, and momentum, Child's law, Bohr's law, all the different laws derived from the universe. And after that, well, you have, of course, the Einstein's, E equal mc squared, energy and matter are the same, and gravity is the warp in space-time, and all the laws that come from quantum mechanics. What if it's the other way around? Rather than deriving all these things from the universe is derived from them. In other words, there's some mind that is creating the universe. And we create virtual reality already. You see performers on the stage have already died. They're holograms. So they're virtual. Problem is, do you clap for them after they perform? Because they're already dead. So we do create reality already. Call it virtual reality. Now you need something perhaps more powerful, more, let's say, omnipresent, and you need something that's everywhere, omnipresent. To create the whole universe. Need something smart too, and be omniscient. And these are exactly the words we use when we refer to God. And we need something infinite that can create the finite. And again, we say the mind of God is infinite. So it looks like perhaps science and religion are not only compatible, but also complementary. Now when we say, for instance, there's something we don't understand, say God only knows, well, it's that. Or when we say something happens or doesn't happen, that it would be either fortuitous or deleterious. If it did happen, we say, thank God that happened. Or thank God that didn't happen. Otherwise we'd be up the creek. For instance, you can say, thank God there's a force of gravity to keep us on the ground, otherwise we'd fly off into space. And thank God the force of electromagnetic force is greater than gravity. Otherwise we'd fall through the earth down into maybe a black hole or a singularity. And God only knows what that is. And thank God there's the strong force, otherwise we'd fly apart. And thank God there's a weak part of force, otherwise we'd be bombarded by harmful solar and cosmic radiation and wouldn't have the atmosphere so we can breathe and to protect us from falling objects from outer space. So one could say that we need both religion and science to understand totally how the world works and how you got here. I think I'll stop it here. I'll actually go on later and try to explain that maybe science needs religion as a moral compass, because science is so powerful now it can do harm as well as good, and it needs something to constrain it, or to make sure it's used for good rather than bad. It already is, of course, but it could be worse as science becomes even more powerful. We now know how to genetically modify humans, and we now use telecommunications to monitor everything that goes on in the world. And these are two areas that we have to be somewhat careful. Otherwise, we could lead to very deleterious effects. End of the story for now.